Hello class, this is Ms. Martins and we are in Unit 7 Solutions. Today's objective is students will be able to develop connections between the pH scale and the amount of hydronium ions present within a solution. Quantify the change in pH scale in terms of powers of 10 to an accuracy of 50%. What does pH even measure? Remember, pH stands for power of hydrogen, so it measures hydrogen concentration, otherwise known as H+. Before we go into pH, I just want to recall and refresh a few basic information about acids and bases. As I was going through the Google Forums, I can see that students still have issues with understanding and grasping the concept of acids and bases, so I would like to review that a little bit. So remember, acids donate protons or H+, whereas bases accept protons or H+. The acronym BAHAD can help you remember this. Bases accept while acids donate. Acids. The Arrhenius definition, Arrhenius was a chemist, for acids was when in water, acids give off H+ as they break apart. H+ is equal to a hydrogen ion, which is also equivalent to a proton. The alternative definition, which is known as the Bronsted-Lowry definition, is that acids donates protons. You have to be an acid to donate a proton. So this is the Bronsted-Lowry definition, the alternative definition for an acid. Bases. When in water, bases give off OH- as they break apart. This is the Arrhenius definition for bases. Once again, when in water, bases give off OH- as they break apart. OH- is a hydroxide ion. You can find this information on table E. It is a polyatomic. The alternative definition for a base is that bases accept protons. They accept hydronium ions, hydrogen ions. This is the Bronsted-Lowry definition. Distinguishing between the main definition and the Bronsted-Lowry definition is very essential in answering some acid-based questions. Remember the acronym BAHAD to recall that bases accept protons, whereas acids donate protons. So I'm going to go through a few of the Google form questions because I see that there was a common issue with all of them. So the first question is, given the equation representing a reversible reaction, reversible means that the reaction goes both ways. As you can see, there's a double-sided arrow. CH3COOH plus H2O yields CH3COO- plus H3O plus. According to one acid-base theory, the two H plus donors in the equation are. So what does it mean to be an H plus donor? That means that we're looking for the acids within this chemical reaction, right? So how I'm going to go about this is I'm going to focus on one chemical formula in the reactants, which is CH3COOH. Then I'm going to see what happened with that CH3COOH. It went from CH3COOH to CH3COO-. A hydrogen was lost. A hydrogen was donated. Therefore, that is going to be our acid, right? And one thing that I want you guys to note in the questions that I will be giving you, we're going to have at least one acid and base in the reactants and one acid and base in the products. So if I found my acid, I can assume that this will be the base. But just in order to double check, we're going from H2O to H3O plus, right? We gained the hydrogen. Bases accept protons. Therefore, H2O is going to be a base. So this is our acid and this is our base. Now another shortcut for finding the other acid and the other base is, because we know that CH3COOH is our acid, we can assume that CH3COO- is going to be the base. And just to double check this, CH3COO- going back the reverse reactions to CH3COOH has gained a hydrogen. It has gained a proton. Therefore, this is going to be the base. And looking at hydronium, H3O plus, it went from H3O plus to H2O. It lost the hydrogen. Therefore, this is going to be our acid. It donated a hydrogen. So our answer for this question is B. CH3COOH and H3O plus are going to be our acids. Now let's move on to the next question. The next question that had a lot of discrepancy was number 4. The two acids in this chemical reaction, HNO3 plus H2O, yields H3O plus NO3 are what? Right? So first I'm going to look at HNO3. HNO3 is going to NO3 minus. A proton was lost. We don't have a hydrogen here, but we have one here. So a proton was donated. HNO3 is going to be our first acid. And because this is the acid on the reactant side, I'm going to assume that this is going to be the base, right? So if this is the base, let's double check. H2O going to H3O plus. It has gained a hydrogen, gained a proton. Therefore, this is our base. And the same going backwards. If this is going to be our base, I can assume that H3O plus is going to be the acid, because going backwards, I'm going from H3O to H2O. So it lost a hydrogen. Therefore, this is going to be our acid because it donated a hydrogen. So our two acids within this chemical reaction are going to be HNO3 and H3O+. The answer is D. For number 5, the two bases that accept protons are. So I'm going to start with this first chemical formula here, SH minus or HS minus, and it's going to S2 minus. It donated a proton. A hydrogen is lost because we have one hydrogen here and no hydrogens here. So this is going to be our acid. Because this is our acid, I can assume this is the base. But just to double check, we have NH2 going to NH3. A hydrogen was added. It accepted a hydrogen. Therefore, this is going to be the base. So this is our acid. This is our base. And because this is the acid, I can assume that this is going to be our base and this is going to be an acid, right? But just to double check, S2 going to SH has accepted a proton. So S2 is the base, and NH3 going to NH2 has lost a hydrogen. So that's going to be our acid. So the two bases that accept protons within this chemical reaction are S2 and NH2. Now, for the next question. In the reaction, NO2 plus H2O yields HNO2 plus OH minus. The NO2 acts as, so what is NO2? We have NO2 here, and it changes to HNO2. It accepted a hydrogen, so that's going to act as a base. So I can automatically remove answer choice A and answer choice C. But what kind of base is it? Because it accepted a hydrogen, the Bronsted-Lowry definition states that bases accept protons. They accept hydrogen. So therefore, the answer is B. The alternative theory, the Bronsted-Lowry theory, states that bases accept protons. The arrhenius acid is a separate definition, which is in the beginning of the video. You can go back to double check that. Now, number 10. Given the reaction HX plus H2O yields H3O plus X minus, based on the equation, HX would be classified as what? So we have HX here, and it's going just to H. It loses a hydrogen, right? It donates a hydrogen. So the answer is going to be C. It's an acid because it donates a proton. This is just a definition question, understanding the definition, and just knowing how to work it. If you're having trouble with these questions, I recommend watching this portion of the video over and over and over again until you understand it. It just takes practice before you can really grasp this material. I'm also going to be going live at least twice a week, maybe once or twice a week. So if you have any questions, please meet me on Google Meet, or you can email me. I'm always here. Just let me know. Now moving on to pH. The strength of acids and bases is measured on a scale called the pH scale, which is shown in the figure below. The stronger the acid, the lower the pH. So our more acidic solutions have a low pH. In the figure below, battery acid is a stronger acid than orange juice. Battery acid is here and orange juice is here because battery acid has a lower pH. So battery acid has a lower number pH, therefore it's going to be more acidic than the orange juice. The exact opposite is true for a base with lye. So lye is going to be our most basic solution on this scale. So take a second, read the scale, try to analyze the scale. Not all acids and bases are created equal. Consider the two acids, vinegar and battery acid. Vinegar is weak enough to safely eat on a salad, while battery acid is strong enough to eat through skin. Bases also exist along a spectrum. Bleach is much stronger than eggs, right? So just try to look at the scale. The more acidic solutions are going to be on this side. The more basic solutions are going to be this side. The neutral solutions have a pH around 7. This is another image that you should take a look at if you're having difficulty understanding the pH scale. By definition, pH represents the acidity or hydrogen ion concentration of a solution. H plus can also be written as H3O plus, which is also called hydronium. Pure water, which is neutral, has a pH of 7. With the higher the concentration of hydrogen ions, a solution is more acidic and has a lower pH. Once again, the higher concentration of hydrogen ions, so the more hydronium or hydrogen within a solution, the solution is going to be more acidic and have a lower pH. Acids have a pH less than 7, and the strongest acids have a pH close to 0. Bases have a pH greater than 7, and the strongest bases have a pH close to 14. It's important to realize that the pH scale is based on powers of 10. 1 pH unit equals 10 times. For example, a solution with a pH of 8 is 10 times more basic than a solution with a pH of 7. And a solution with a pH of 9 is 100 times more basic than a solution with a pH of 7. And I'm going to explain this here. So pH unit, hydronium changes by a factor of 10, right? So if I'm going from a pH of 2 to a pH of 3, my hydronium concentration has depleted by a factor of 10. If I'm going from a pH of 3 to a pH of 4, my hydronium concentration has depleted by a factor of another 10, right? But if I'm going to 3 to 5, our hydronium concentration has depleted by a concentration of 100. So going from two values of pH that are, so 3 to 4 would be 10, but 3 to 5 is 100. 6 to 7 is 10, 6 to 8 is 100, 6 to 9 would increase by a factor of 1,000. Okay? So I'm going to put that into practice. We're going to see how to answer questions that are based on pH and looking at hydronium concentration versus pH using these success criteria. First, we're going to determine how many pH units it changes by. Then we're going to determine change in factors of 10. So if it's 1 pH unit, that's a factor of 10. 2 pH units is a factor of 100. 3 pH units is a factor of 1,000, so forth and so on. Determine if the pH is increasing or decreasing. So if we're adding more hydronium to the solution, it's going to become more acidic, meaning that we're going to decrease our pH. If we're removing hydronium and there's less hydronium or hydrogen within the solution, we're going to increase the pH because it's becoming more basic. Now, the first question that we're going to answer in order to understand these concepts are, if the concentration of H plus hydronium increases. So if we're adding hydronium, what happens to the pH? If we're adding hydronium, it's going to become more acidic. So take a moment, pause this video, and try to answer this question. If we're adding hydronium, which is more acidic, what happens to the pH? If you guess decreases, you're correct. Acidic solutions have a low pH. So if we're adding hydronium, which is more acidic, our pH will decrease. If the concentration of H plus changes by 1,000-fold, how many pH units will it change by? So if it's increasing, if the concentration of H plus changes by 1,000-fold, that means that it's changing so 10-fold would be 1 pH unit, 100-fold is 2 pH units, 1,000-folds would be 3 pH units. So make sure that you understand how to do that. If we're changing pH units, every 1 pH unit is 10. So we're just going to keep multiplying by 10 to get to the number. If the pH of a solution is 3 and the concentration of H plus is decreased by 100-fold, what is the new pH of the solution? So I'm going to read this question again. If the pH of a solution is 3 and the concentration of H plus is decreased by 100-fold, what is the new pH of the solution? So we're starting off with a solution of 3 and we're removing hydronium. So the solution is becoming more basic. That means our pH is going to increase, right? It's going to increase by what? 100-fold. So 10-fold will bring up our pH to 4. 100-fold will bring up our pH to 5. If the concentration of H plus changes by 1,000-fold, this is the same question from before, so I'm going to skip ahead. Question 1. When the pH of an aqueous solution is changed from 1 to 2, the concentration of hydronium ions in the solution is. So we're getting more basic, right? What is happening to the hydronium? The hydronium is depleting. So our answer is going to be between 1 and 2, right? It's decreasing. Our hydronium concentration is decreasing because we're getting more basic. And we know that if we're looking at hydronium concentration, the factor is changing by 10. So our answer will be 2. Question 2. Which change in pH represents a 100-fold increase in the concentration of hydronium ions in a solution? So, which change in pH represents a 100-fold increase? A 100-fold increase means that the pH is going up by 2. So we're increasing the hydronium concentration. So instead of going up by 2, our pH is actually going to decrease by 2, right? So the answer is not 1 because it's getting more basic. The answer is not 3 because that's only a concentration increase of 10-fold, not 100-fold. Our answer is going to be 4. So this is the a section, a screenshot of the worksheet that I'm going to have you guys work on. The exit ticket, I would like you guys to complete the worksheet found on Google Classroom. I will post the answers later in the day, and I'm going to add a Google form with practice questions so that you guys can understand the concept a little better. If you have any questions, email me or write in the comments of the Google Classroom. Stay safe and be well. Thank you.